Thank you very much for the introduction. So today we're going to talk about two interesting things from the NLP domain, which is topic detection and transformer models. So first things first, let me introduce to yourself. I'm Tomasz. I'm a software engineer by training and data scientist by heart. I'm currently finishing my master's degree in computer science at FU Berlin. I'm also writing my master thesis here at Axel Springer NMT about topic detection. Now, I'm also the member or working student at the content intelligence team, where we are doing some amazing work. So basically, NMT is responsible for all the tech standing behind WeLT and BILD. At content intelligence team, we deliver insights, like in real time. We work closely with editors, publishers, journalists in order to equip them with data-driven tools to help them do their job. This applies to analytics dashboards, tracking performance of websites or articles on BILD.de, as well as Slack bots running ML algorithms to automatically inform editors about, for instance, potential issues. So thanks to our close relation with the editorial teams, we are aware of problems and challenges they are facing on a day-to-day basis. So one of such problems is definitely, what should I write about? BILD and WeLT together publish around 11,000 articles per month. Undoubtedly, there's a lot of going on, a lot of news, possible topics and events to cover. But journalists often wonder how to decide what is really important right now for the viewers and what has already lost its urgency. So in the past, decisions like that were dictated even straight by the agenda or the journalist's intuition. And this made us think that maybe instead of measuring the performance of particular articles alone, we should rather take a step back and look on the articles from a topic perspective. Such perspective will enable us to look at the groups of articles covering similar events or topics. It should also allow us or the journalists to distinguish between topics that are rapidly losing on interest for the people from the ones that are still, let's say, hot. And here, let's reveal our first use case, which is a dynamic topic analysis. What we have here on this diagram is a beautiful example of a topic lifecycle. This diagram is showing the performance of 5 articles in terms of page views. These 5 articles are about the same event, which happened to be a knife attack in Nice in October 2020. As you can see, that the very first article published covering that story were actually pretty successful. However, 3rd, 4th, and 5th did not came even close. Seeing this chart, you can ask yourself if writing the 4th and 5th article about that event was actually the best possible decision. Considering the steady decline, it might have been better to rethink it and maybe write about something else, because this topic is actually dead and it's simply time to move on. So being able to cluster out the articles automatically in that way would enable publishers to decide which articles should be promoted, and editors would help them to gain a better intuition. So what is worth to write a follow-up story about? So to sum it up, we want to automatically, programmatically extract the topics from our articles. Secondly, we need to be able to name these topics in a proper manner. So every topic should be unique and should be apparent for the user. Using keywords, it should be possible to identify this topic without need to look on what the articles are within the topic. Next, considering this large volume of articles coming in every day or week, the topic modeling has to deal with them on the go, and it should run continuously. And lastly, we need to do some data integration in order to compare the topics among each other and see see what is the most important thing right now. So to address these challenges, I think the best answer is topic detection, or often called as topic modeling. Now, what is topic detection at all? So I think before we answer that question, we need to answer another one. What is a topic. So topic is nothing else but a set of words co-occurring together in the same context, nothing beyond that. And a topic detection is an unsupervised machine learning problem. It discovers abstract topics that occur in a collection of documents, which we call corpus. And it is often used as a text mining tool to reveal semantic structure within a body of text. So now, how do we model topics? So this research in this field dates back to late 90s. So the most classical and powerful examples are LSA, latent semantic analysis, and LDA. So they both, however, carry some inherent limitation, which makes it rather unfeasible and not very scalable. The most important limitation of these approaches is the fact that they require fitting the model every time the new article is added. And these arguments have pushed me to explore a different family of approaches, which is embedding-based topic modeling. These approaches are based on document clustering that is working behind the scene. So now, first, what are the embeddings, right? So embedding is just a numerical representation of the data that has meaningful distances between the points. This numerical representation spans a vector space, a feature space, in which location of the points carries some meaning. I bet that many of you have heard about word embeddings like word2vec, which is a type of a word representation that allows words with similar meaning to have similar representation. Now, today we are going to talk about something bigger, and namely a document embeddings. So in order to represent document, we could use different techniques. The most classical ones is definitely bag of words, in which we just represent a document with as a simple list of strings that are being from a vocabulary that are being converted to numbers. We can go a little bit more fancy, and instead of these numbers, we could use vectors, for instance, using doc2vec or fast text. Or we can also be this, however, was the research has proved that this is not the best solution to do so, and there are better approaches that takes, for instance, context of the words that are being used into consideration. Therefore, I decided to look at something called transformer-based embeddings, and the most prominent example of these is sentence BERT. Now, let's talk about architecture of our system. So we know what are embeddings right now, but besides embeddings that are representing the documents, we have also other components in our system. So this diagram shows all the processing steps that take place from loading the articles until we have a clear mapping between article and a topic. It goes from preprocessing to encoding, dimensionality reduction, up to clustering and summarization. And we will go over each of these steps in detail right now. So first, let's start with the data. What we have at the very beginning, we have basically articles. An article consists of headline, which is something about Heidi Klum. We have department, which is a category of that article. Could be gossip, could be sport or politic. We have a CEO title, which is a less clickbait of a title than the normal headline. And it actually contains a lot of information about the content. And of course, we have the body of the article. Besides that, we have some metadata like created at, which is the date the article was published. And we have two important things. So we have named entities. So in information extraction, a named entity is a real word object, such as person, Angela Merkel, location, Berlin, organization, BMW, or product like S-Class. These objects can be donated with proper name and have some physical or abstract existence. We are using Google NLP API to extract those entities for every article and title. And please keep that in mind for now, as we are going to be referring to them later on. So Once we read the articles, we have to process them. So NLP and dealing with the text can be very, very messy. So in order to put the text data in the right shape, we have to apply tens of string transformation to remove all the unwanted stuff from the text. Stuff like currency sign, some weird Unicode characters, an extensive punctuation, tags, and so on and so forth, or URLs, or email addresses. So the ultimate goal is to make these articles resemble a chapter of a book without any fancy additions from the editors. And at this step, we also do one interesting thing, which is joining the title and the body of the article together, because title actually entails a lot of information about article content, and it would be a loss to just let it go. So now, as we have beautifully cleaned articles, now we need to start encoding them or turning them into numeric representation. So this representation has to have a few qualities for our project to succeed. We need to assign fixed size vectors to every article, so it's just easy to compare them. Secondly, it has to encode similar meaning articles in a similar way, so these articles land close to each other in a vector space. And lastly, it has to be very performant, quick, and ideally easily comparable with a distance measure like cosine, which is very often used in the NLP field. And at this stage, we could use various document embeddings that I have mentioned earlier, but based on my research, I decided to use a fancy transformer-based model called sentence BERT. So transformers in general, or BERT, has set a new state-of-the-art performance on the sentence pair regression or different tasks like semantic textual similarity and so on and so forth, text classification. These models generate contextualized embeddings for input tokens, or rather commonly subword units, each infused with the information about the neighborhood. So each infused with a context the word is being used in. This model, however, is not perfectly suited for generating like rich embeddings for the whole input sequence, but rather for the token itself. So sentence BERT is an architecture that adapts the classical BERT to do this task. And it uses a Siamese architecture to derive semantically meaningful sentence embeddings. Then that can be then compared using cosine similarity. Now let's take a closer look how it works internally. So this diagram shows that shows actually a fine-tuning, or rather training step of a sentence BERT model. To fine-tune our network, we need to somehow tell it which sentence pair are similar and which should be close in the vector space, and which also should be dissimilar and far away in this vector space. For that, we have to have a long list of pairs, sentence pairs, or document pairs, short document pairs, with a score assigned to them, like 0 or 1, that denotes how similar is the pair. So sentence A, B, and then score 1 would be a perfect example. And one such pair is visible on the bottom of the screen. We can see that these two sentences about a birdie are almost identical in meaning. Therefore, I would expect it have to have a very high similarity score. So in the training step, this pair is fed in parallel to two pre-trained BERT models. In production, we use, of course, German BERT because we are dealing with a German text. And these two BERT models share a lot of their trainable weights with each other. And these BERT are used to generate this contextualized embedding for words. And next, these embeddings are being pulled or basically kind of averaged with some, let's assume just averaged, and passed further. Lastly, in the final step, these sentences are fed to cosine similarity function that measures the distance of these two vectors and compares this distance score with a true labor. In order to maximize that distance for similar pairs, we use something called cosine similarity loss, which penalizes the model in a case the cosine similarity for our pairs is too big, or too small in case we're talking about two different sentences. So now we know how this sentence BERT works, and after training, we basically just need a half of this architecture to use it for generating this cosine similar phrase.
You are muted, Tomasz. Out of a sudden, you are muted. I don't know why.
Oh,
now you're back.
Thank you, appreciate it. So I hope you heard, we were talking about that we have now vector representations that are contextualized for every document we started with. And these vectors, however, are very high dimensional. And this could be a problem considering that in the later stages, we have to cluster these vectors. So we need to reduce the dimensionality from the initial 780 features to something around 100. Otherwise, we would fall into the curse of dimensionality. The more dimensions we have, the closer is the average distance between two random selected points. So for that, I decided to use UMAP reduction, dimensionality reduction, as it has one important benefit in comparison to other strategies, like, for instance, PCA. Namely, it uses a predefined similarity function to measure distances between the points, and then it uses the same function to preserve these relative distances in this lower dimensional space. And after dimensionality reduction, we add some additional features like the department, which is one hot encoded and a time step. And after that, we end up with very nice vectors, nicely describing the semantics of the article. So in order to get the topics out of it, we have to cluster these vectors. And for that, we use HDBSCAN, which is a hierarchical and density-based algorithm. Density-based means that we don't need to know the number of the articles beforehand. We let the algorithm to figure it out by himself. And hierarchical means that we can control the size of the topics, which means we can control the homogeneity, or how homogeneous we expect the topic to be, which in practice would mean, do we want to have all the football articles clustered together, or do we want to have Bundesliga, Champions League, and Bundesliga 2 in a separate cluster? Just by basically cutting this hierarchy and at the right spot, we find it correct. Now, in the final step, we have already clusters, and we need to derive topics from those clustered documents. For that, I came up with a class-based or cluster-based variant on TF-IDF. So you probably remember this name entities I mentioned before. And now let's treat all the articles in a single cluster as one big article and combine all the named entities of these articles into one long list. As a result, we end up with a few long lists for every for every cluster, which we then apply TF-IDF on those lists in order to select the most meaningful words describing a cluster, which we then store in our database to use it further in a downstream application. And now, I think demo is worth 1,000 of slides, so let's quickly jump to it. So in Metabase, which is a graphical user interface sitting on top of our database, we created a dashboard that allows publishers, journalists to actually explore topics or explore what topics were covered in the previous week. And this diagram dashboard actually shows 1 week, actually last week of March, I guess. Yes, that's it, with the beginning of April. And what they can see here is the top topics in terms of page views, what is in these topics, and how this popularity of these topics decreased or stayed. And let's take the very first one example from about Merkel and giving an interview to Anne Will, which happened sometimes in March 2000, something in 29th March. And we can see a steady decline, but it's not like it wasn't like the case that I showed at the very beginning. So here one can learn that actually it might have made sense to actually write some more articles about that topic in the middle of this time range, which was around 1st of April. And yeah, that's how it looks like. I think I don't have much time left. That's why I would like to thank everyone for the attention. And in case you have any questions, this is the time to ask them.